In this video, the last video of the lecture for section 4.3 on linear independence of vectors, we want to see a little bit more about how to think about linear dependence versus linear independence and wrap up with a few examples. So here you'll notice I'm saying we want to consider the span, all the linear combinations of linear independent vectors v1 and v2, thinking of it in R3 just for convenience. So if we think about a vector v1 in black here and v2 in black here, any linear combination of those two wouldn't be in the span of these two vectors. But any linear combination of these two vectors is just some c1 times the v1 vector, so some amount in this direction, plus c2 times v2, so some amount in this direction. And if you graphically add those vectors, you can see you're still going to land in the plane defined by these two v1 and v2 vectors. Right, so any vector v in the span of v1 and v2 really visually just looks like it sits in the plane defined by v1 and v2. Right, any vector in the plane is in the span of v1, v2. In other words, it's just a linear combination of v1 and v2. But keep in mind, that means only vectors that point kind of outside of this plane. Let's see if we can draw one pointing outside the plane. Maybe here, this vector is perpendicular. Doesn't have to be, but I'll do that for depth. This vector, I'll call it u, looks like it would be pointing out of the plane, not in the plane, not parallel with the plane. So only vectors outside the plane wouldn't be in this span, wouldn't be a linear combination of v1 and v2. But since we know that linear independence requires no single vector is a linear combination of the other, this fact here tells us that any vector that sits outside the plane, since it's not a linear combination of v1 and v2, could be taken along in a set with v1 and v2 to yield a new linearly independent set. So visually, my point in pointing this out is to say this, that from this picture we can sort of see that if you have an independent set of vectors, it means that the space spanned by the vectors somehow, I'm going to write this kind of loosely, gets smaller if we remove a single vector. Right, in the example we mentioned above, taking v1 and v2 along with this u that points outside the plane, that's three linearly independent vectors. But if we got rid of just one of those, say this u out here, the space that we can span with these three gets smaller. We're trapped in the plane now if we get rid of u. But so long as we have u, we could actually describe anything in the plane and anything off the plane in the direction of u. So having that third vector kind of outside of the plane defined by v1 and v2 makes the space bigger that we can span. If I get rid of any one of those three linearly independent vectors, the ones I have in black here, the space I can span by the remaining ones gets smaller. It goes from 3D space down to a plane, for example. Another fact to mention here is, kind of on the flip side, a dependent set of vectors implies that at least one vector could be removed without changing the span of the set, without changing that space that we could cover with the remaining set, with linear combinations of the remaining set of vectors. So a dependent set implies that at least one vector can be removed, pardon my handwriting here, without changing the span of the set. right? For example, if I think about v1, v2, and now this v that I said was already in the span, meaning the set of all three of these vectors, v1, v, and v2 together, that'd be dependent, because this v here is a linear combination of v1 and v2. But if I take all three of those together, I notice I could toss out any one of those, and I'm still describing the same plane with the two that remain. The plane swept out by the two remaining vectors is still that same plane. And that's true of all dependent sets. If I remove it, if I've got a dependent set, there is at least one vector, at least one vector that can be removed without changing the span, the space we can actually cover with linear combinations of those vectors. So a couple examples here. Let's see this example first. Let's do this up here. Let's ask, is the set of vectors 1, 2, 3, -1, -1, -1, 1, -3, -4, and 1, -2, -10 linearly independent? Right. The immediate answer, I would say, must be that no, these are not linearly independent. Why is that? Well, thinking about these 4 vectors in R3, I know R3 is a 3-dimensional space, so any 3 independent directions will let me cover the entire space. I've got 4 of them here. At least one has to be an extra direction that could be described in terms of the others. But how would we show this if we weren't trying to be that clever about it or think that hard about it? How could we see it with the kind of the long way around? Let's call this the long way. If we want to know if this set of vectors here, these 4 vectors, is linearly independent, well, we just remember what that really meant by definition, aside from all the intuition. What was the definition of linear independence? The definition would be that C1 times one of the vectors plus C2 times the next vector plus C3 times the next, all the way out to C4 times that last, would have to equal the 0 vector, right? When we set this up, if our set of vectors is linearly independent, that means there is a solution to this other than just all 4 scalars being 0. So can we find, we'll say it's linearly independent, independent, missed my N there, linearly independent only if C1 through C4 are not all 0. Sorry, mixed it up. Are all 0. Refer back to that definition there. All right. If all those scalars have to be 0 for this linear combination to be the 0 combination, that means these are all independent. Right? There's no one that we could do without and still span the same space. So let's take a look. Let's see how we would solve this system. Usual setup, I'm going to jump right to the, well, let's write it out, I suppose. Equating components, we get C1 times 1, really minus C2 plus C3 plus C4 must be 0. That's from equating the first components of both sides of the equation. 2C1 minus C2 minus 3C3 minus 2C4 Yikes. Two C4 would have to equal 0. That's from all the second components. And third components, 3C1 minus C2 minus 4C3 minus 10C4 would also have to be 0. And we can pack this right up into an augmented matrix to see what the solution will be. Just writing it out as usual. That's our augmented matrix. And when I reduce this down, I get this result. Oops. One zero zero negative 29 thirds comma 0. 0 1 0 negative 37 thirds 0. And finally 0 0 1 negative 5 thirds 0. And again, I'll let you just check that for yourself. Oops, check the computations there for yourself. Sorry about that. But this is what I get. And notice if we unpack this, it says C1 equals 29 thirds of C4. C2 equals 37 thirds of C4. C3 equals 5 thirds of C4. And C4 is just itself. So at this point, we typically replace that free variable C4 with the parameter. So let's do that. Just erase all the C4s, write them as parameters R instead. Oops. R, 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 and C4 is what we called R. So then we get that any real number R plugged into here would give us a solution. Certainly R equals 1, for example, gives us a solution other than all zeros, right? So it's not true that this is linearly independent. For linear independence, we would have to get all zeros out for our solution. We did not get that. There are non-zero solutions to this system, non-trivial solutions. So we can conclude. Let's see. We conclude that since C1, C2, all the way to C4 are not all 0, this set is linearly dependent. Well, that was kind of longer than I expected to take, so maybe we'll do one quick last video to wrap up after this.